All right, so here are some notes for 19.1 through 19.2. This is going to be a pretty short video, but it goes through two of the bigger concepts that we need to understand as we get into dealing with DC circuits and building circuits. After this, it's kind of a re-application of some stuff that hopefully we understand about Ohm's law and just a different application for capacitors. But so first off, a couple of things that you're going to need to understand or acknowledge. We have a couple of different symbols that we want to recognize as being relevant. When we have this double line, one longer than the other, that means it's a battery. It'd be typically a DC source. The positive terminal is the bigger side, and the negative terminal is the smaller side. We have the symbol for a capacitor. I'll always use this double parallel line, but some books will use, or some notation will use a curved line for the capacitor. Resistor is always our zigzag line here. A wire is just going to be a straight line. If you see a wire going around, that's just a straight line. If you ever see this symbol here, it represents a switch, which means it's like an on-off switch, where you can close the circuit or not. Then you have ground symbols. When something is grounded, we'll show that symbol where its ground is connected. So that's important as well. I've seen this triangle symbol used a few times, but not very often. So first thing we need to understand as we get into talking about circuits and defining them is essentially what we call voltage. We've talked about voltage as this charge difference and this potential difference between the two charges and how electrical charge wants to move from one to the other. Whether it's a battery or something else, there was this sense of that there was something causing things to move. If you think about a generator or a motor, you put electricity to it and a voltage to it, and it seemed to cause motion. And so this concept of electromotive, so electrical motive force, but it's not really a force, but that's how it was understood at the time. Like there was something that caused this motion, and so they called it the electromotive force. Essentially, was initially going to be measured in. It's not the same thing as a force, and so they didn't want to call it a force because that led to confusion about is it measured in newtons or not. The truth is the electromotive force is measured in voltage. And so they decided to start just calling it EMF. And so you'll use this symbol, you see this symbol, funny script looking E that represents the EMF. Essentially it's the voltage between two terminals, so a positive and negative terminal of a battery. At the end of the day, if you see EMF or electromotive force, understand that it's the voltage on the battery, how much battery voltage we have that causes movement. Now, we have to understand is that batteries themselves do not always give us the same voltage. Depending on the circuit that they're hooked up in and its own personal characteristics, there's going to be a different voltage that's supplied. See, even the battery itself has some amount of internal resistance. And so even though this might be, say, a 9-volt battery, I'm not going to get 9 volts out of it because there's some resistance inside the battery eating up some of that voltage. So we want to understand why or how to determine how much voltage we lose. Well, Ohm's law tells me that the voltage loss through any resistor or component is equal to the current times that resistance. Now, because it's internal resistance, we're going to use a little r, just so we don't confuse it with the resistors everywhere else in the circuit. Well, if I can figure out how much current is flowing through this resistor, then I can figure out was it 0.1 volts that was lost? Is it 0.2 volts? And so from there I can figure out what the actual, what we call terminal voltage is, which is the voltage difference between the positive and the negative terminals. That's after we've lost that voltage inside. What's really interesting is that the voltage is, so that little resistance inside is going to be a set value. It doesn't change from time to time. But this current can go up or down based on how it's hooked up in the circuit. So if a circuit has a lot of resistors in it, it's going to have a very low current, which means that this terminal voltage or this internal resistance is going to make very little difference. But if I hook this up to something that has very little resistance in the circuit, like a toaster or something like that, a light bulb, like so maybe a flashlight has very little internal or very little resistance through the circuit, that means that I'm actually going to lose quite a bit out of the battery because I have such a high current that I'm going to have a bigger loss in the battery. And so depending on the circuit that you're working with, you need to first find the current that flows through the battery, so that you can find the terminal, so you can find the terminal voltage. We'll look at that here in just a second. I'll do a quick example problem of that when we're done, because there's a couple of things we're going to have to deal with that important that you understand. So let's scroll down here. Let's talk about our second set of rules. When we have resistors, we can compile them in a combination of different ways. And depending on how they're compiled or put together, we can get very different results in terms of the current that's produced. Now think of the resistors maybe as doorways down a hallway. If I put multiple doorways, right? So you know when you go through a doorway in the high school, it sort of slows traffic or slows flow of people through the hallway. Every time they go through an entranceway, it's going to slow them down. You're going to get sort of a pileup. Well, if you put one door here, let me grab my pen. If I put a door here, and then a few feet later I put another door, and a few feet later I put another door, that crowding is going to affect the flow of people significantly. It turns out that when we put resistors in series, which means one following the next, okay, the total resistance, or the equivalent resistance, is equal to each of the resistances added up. Meaning every time we go through one of those doors, it's going to affect us, and the next one will affect us very similarly. So if you had a 3 ohm resistor, a 2 ohm resistor, and a 5 ohm resistor, we'd add those up, and we'd say the equivalent resistance to that whole circuit, if you put one light bulb in, it would have a 10 ohm resistance. Okay, so that's pretty straightforward. When they have them in a straight line like that, or in a sequence, we can just add them up. But if we were to take those same doorways, okay, I want you to think about that flow of traffic again. If I put a doorway here, a doorway here, and a doorway here, and people could flow through that door, or that door. Okay, they go through any door, but they're all in parallel. We just pick a path. Would the flow of traffic be better or worse? Well, I think it would be significantly better, because people would spread out and find their way through those doors, and we'd see that the current, or the flow there, is going to increase. We're going to have less resistance. So when we have a circuit with the resistors in parallel, which looks a lot like these, you can see how as I'm coming along, I get to this junction and I have choices. That as I go through any one of these choices, because of the fact that I can choose which one I want to go through, okay, I will say that the R equivalent, the equivalent resistance for that whole circuit, if I just replace all the light bulbs with one light bulb, it would equal 1 over R1 plus 1 over R2 plus 1 over R3. And I could keep doing that as many times as I want. And at the end, I raise it to the -1 exponent. That's going to flip everything back into resistances. But this is how we add those resistances in the circuit. Well, what that does is that allows me to figure out how much current, and this is the same with the series versus parallel. Once I have the equivalent resistance, okay, then I can figure out how much current flows through the circuit in general. And if I know how much current's here, then I can figure out how much of it will flow through each of these resistors individually. So those are all really important questions. A couple of things that you need to know to make the problems a little bit easier to understand. Let's jump to another page here and add ourselves some space to do some work. All right, so a couple things about resistors in series and parallel. This is really important stuff. I want to make sure we understand when we put this stuff together, because it makes Ohm's law work for us. And remember, Ohm's law says the voltage through any component is equal to the current that flows through that component times the resistance of that component. Well, let's say, first off, that I have a battery, and let's give it some internal resistance right there, and then let's just hook it up to a light bulb. Okay? And we'll say the resistance of this light bulb is 7 ohms. We'll say, and so I'm going to put a dot here and a dot here. That represents the terminals of the battery, and then this little R here, let's say that it has 1 ohm. Okay? And let's give ourselves a voltage of, say, 8 volts. Let's make this really easy to calculate. All right, so I've got 8 volts supplied to the circuit. I've got a 7 ohm resistor, but I've got this internal resistance of 1 ohm. So the first question is, how are these resistors connected? Are they in series or are they in parallel? Well, because there's not a junction that gives me choices or paths to follow, it's one big cycle all the way around, right? There's not multiple paths. That would make them in series. And so the equivalent resistance for this circuit would be 1 plus 7, or 8 ohms. Now I can use that total resistance to calculate the current that flows through the circuit. As long as there's not a junction, that current will never change throughout the circuit. Well, using Ohm's law on the whole, so voltage equals current times resistance. So I'm using this for the entire circuit, which means the total voltage was 8 volts. The total current is unknown, but the total resistance is 8 ohms. Well, this would tell me that the current that must flow through the circuit would be 1 amp. All right. Now that I know that 1 amp goes through the entire circuit and it just continues, that's the rate at which the current flows. That means, because there's no extra path, that 1 amp flows through my internal resistor of the battery. So then for the battery, okay, the voltage loss at the battery would equal the current, which is 1, times the resistance, which is 1. I would have a voltage loss in the battery of 1 volt. So the voltage that's being supplied to the circuit in general, okay, what we call the terminal voltage, we'll use an AB to represent from point A to point B, the terminals of the battery. The voltage will equal 7 volts. I had to remove the voltage that was lost inside. Okay, so that's how we can use series connections to help us understand the terminal voltage on a battery. Now, if I had hooked that up, let's say I hooked this up not to a 7 ohm, but let's imagine that this was a 15 ohm. Okay, if that was the case, so I'm changing the problem now, my total resistance would have been 16 ohms, and V equals IR, I would have had 8 equals I times 16, so current would have been 0.5 amps. Well, if I take that 0.5 amps and I plug it in for my voltage on the battery times my resistance of 1 ohm, that means my V loss would only be 0.5 volts, so my terminal voltage, AB, would be 7.5 volts. So by using bigger resistors in the circuit, I reduce the amount of loss due to the internal resistance. But I do also have a smaller current, so the light's not going to be as bright if it was a light bulb, because there's less flow of electricity. So, you know, internal resistance depends on how the circuit's built from outside of the battery, not just what's going on in the battery. Let's take a look at a couple of problems that we might need to address on the homework today. So let's say we've got a resistor here, maybe a resistor here, and then let's make it a little complicated. Let's go resistor here and resistor here. And let's say that this is a 12 volt supply with a 3 ohm resistor here, a 2 ohm resistor here, an 8 ohm resistor here, and a 4 ohm resistor here. And I want to know what is the voltage on the 2 ohm resistor. Okay, what's the voltage loss across that resistor? So to do that, I'm going to need to know the current that flows through that resistor. Well, to know the current that goes through the 2 ohm resistor, I've got to start by figuring out the current that's supplied to the circuit in total, which means I've got to find the total resistance and the total voltage. So sometimes we think about this, you know, on the circuit level, and then we're going to do components. Okay, so there's V equals IR here on the whole circuit, and there's V equals IR on the components. Well, I know the resistance of my component is 2, but what I don't know is the current in order to find the voltage. So I'm going to have to go find the current. To do that, I have to start by finding the total equivalent resistance. Okay?
Just a reminder, remember all track people, track will start in the Commons at 3:45 after school. Track in the Commons after school. Thank you.
All right, so we're almost there. If we look at this circuit, we have to recognize what's in series and what's in parallel. So this 3 ohm resistor and this 2 ohm resistor are in series, and they're in series with this whole thing here. Okay, you see 1 plus this plus this. All right, so 3 plus 2 plus, I need to figure out what this parallel thing is actually worth. To do that, I'm going to build the parallel rule, which is 1 over 8 plus 1 over 4, all to the negative 1. All right, this is going to give me the total resistance for the circuit. I'll grab my calculator, and let's put that in. I'm just going to do the parentheses first. 1 over 8 plus 1 over 4. Close my parentheses. And I just hit a negative 1 exponent. It gives me 2.6 repeating. And I'm going to add the 3 plus 2, which is 5 more, to get 7.67. So we'll go with 7.7. So R equals 7.7 ohms total. Well, the voltage is 12 volts. The current is an unknown current times 7.7. So the current total equals 12 divided by that answer, which is 1.57. And if I bring that number over, now this is really important. We have to decide if we're losing our voltage, if the current is all going through this resistor or if it's been split. The way that you know if the current has been split is if you're in a parallel path. As we go through this 2 ohm resistor, we are not in a parallel path. If I asked you about the 8 or the 4, the voltage loss there is different to find because not all of the current is going to go through each of those resistors. It's going to split. But because the 2 ohm resistor is a series resistor, I can put all of the 1.57 there. And if I times by 2, I get 3.1 is what we'll go with. So the voltage loss at the 2 ohm resistor is 3.1 volts. Now let's say that I did want to find the 8 or the 4. The best way or the simplest way to find the voltage loss would be by finding the voltage loss at the 3 and at the 2, knowing that I have to come up with all 12 volts. I have to use all of the voltage the battery supplies. So if I use 3.1 volts at the 2 ohm resistor, if I use, it'd be about 5 volts here, that gives me 8 volts roughly. That means I must be using 4 volts as I come across this last component. And the cool thing is, when you're in parallel, this loss here and this loss here will have the same voltage. So the voltage of the 8 will equal the voltage of the 4. Both of them have the same voltage loss, although they both have different currents. So the beauty of a parallel circuit is you have the same voltage across multiple light bulbs or components. They all end up with the same voltage change. You're going to have questions. We're going to hash it out some more next time in 19.3 with Kirchhoff's loop rules. So let's talk about it then. But understanding this concept of getting around the circuit, using up all our voltage, big deal. We're going to learn a lot about it as we keep working. All right, good luck, and we'll see you in class.